Welcome to the ITP. I'm David Gross, and I'm the director of the ITP. And as you know, we try to bring to the Santa Barbara community every once in a while some of the distinguished visitors who pass through these halls to participate in our programs. A few months ago, we had a lecture by Kip Thorne, that many of you attended, who was participating in our astrophysical program on black holes. And we're also running this semester a program on strong gravitational fields, classical and quantum. And Roger Penrose is participating for a few weeks in that program. So we took the advantage of his presence to ask him to give a public lecture. And he kindly agreed. We're delighted. Roger is the Roos, is that how you pronounce it?
Rouse.
Ball Professor Emeritus at Oxford University and also a professor at Gresham College in London and at Penn State and a visitor at the ITP. He is known throughout the world, as is evident by this audience, for his contributions to many things, to mathematics, to physics, and to fun, to recreational mathematics in particular. Many of you probably know him for his tiling, which has had a major impact on the design of bathrooms. But he also is the inventor, together with his father, of the impossible triangle and other delightful images that appear in Escher's work and art. But when he can take his mind off serious work, he dabbles in pure mathematics, where he's made major contributions, and as far as we're concerned, most importantly, in physics, where he was one of a group of people who revolutionized, really, the study of general relativity in the last few decades, proving very important theorems having to do with the existence of nasty things called singularities. He also is the inventor of something called twistors, which I hope he won't explain to you, and of conformal geometry, a marvelously important tool for the study of Einsteinian relativity. He's also, which is more unique even among physicists, an extremely good popular science writer. He's written, as I'm sure you all know, a book called The Emperor's New Mind, which was one of the few bestsellers in popular science writing. It's a very interesting book. Roger has been highly honored. Among many of his honors are the Wolf Prize, which he received with his close collaborator Stephen Hawking, the Albert Einstein Prize, the Heinemann Prize, the Dioch Medal. And in 1994, he was knighted for his services to science. So I have the privilege of introducing to talk about science and the mind, Sir Roger.
Well, thank you very much, David. My time here has been very enjoyable, but it's just whizzed by. I don't know where it's all gone. It's certainly great to be back in Santa Barbara. Now, I want to get these machines working. Let's try that. Good. My talk is, I think, well illustrated by this transparency here. Now, here I've illustrated three worlds. These are pictures here. And this blue one over here is meant to represent the physical world. So that's the world of physical objects like this gadget here and this one and so on. And here we have the mental world. So that's the world of our perceptions, consciousness, and so on. And in order to talk about these things, I want to talk about them in relation to a third world, which I've called the Platonic world. That means the world of absolutes, but most particularly the world of mathematics. And in fact, if we want to understand the physical world, what we do is to understand it in terms of models, mathematical models. So in other words, it's in terms of things lying up here. Now the arrows in this diagram represent what I call mysteries. So there are 3 worlds and 3 mysteries. And one of the particular mysteries I want to discuss is this one here, which is how it is that when you have the right kind of physical structures, and I refer to things like human living brains, then somehow mentality seems to come about, and that's a mystery. But in order to discuss this, I want to relate it to 2 other mysteries, one of them being this one here, why it is that the physical world seems to accord so precisely with mathematics, and it's not just the precision of the way in which it accords with mathematics, but also the kind of subtlety, sophistication of the mathematics that seems to underlie physical activity. And that does seem to be something mysterious. But I think I want to start also in my discussion with this other mystery, which is how is it that somehow we seem to perceive mathematics, the kind of sloppy kind of thinking that goes on in our brains, somehow seems to be able to access this very precise world of mathematical notions. So let me put that one on this side and keep that one in view. And I'll talk about consciousness, which is what really I mean when I'm talking about the mental world. And one can think of unconscious things as part of mentality as well. But consciousness, seems to me, is the real mystery of mentality. So the question arises, how are we going to understand consciousness? And one of the particular views that people have, it's very popular these days, is that we should understand it in terms of what computers do. So one of the possibilities is that we should understand consciousness in terms of computation. Maybe if you have a device which computes and does the right kind of computation, does it fast enough and so on, whatever it is, that somehow consciousness would come about. And that is a view which is quite strongly held by some people. It's referred to as strong AI, strong artificial intelligence. However, it might be that's wrong. Maybe it isn't. Computation in itself would never produce consciousness. But nevertheless, we would hope to be able to understand consciousness in terms of, well, existing science. We have a very good view of the physical world, not complete perhaps, but at least we have a very, most phenomena we seem to be able to describe in some way in terms of mathematics. But the mathematical theories that we have seem to be pretty comprehensive. So can we understand consciousness in terms of existing science? Or maybe that's not enough, and we're going to have to go to an extended physical worldview, still science, but something beyond the kind of science that we know now. Or perhaps there's something beyond science, and that consciousness is something that it's not possible to get to terms with in terms of purely scientific reasoning and so on. Maybe there's something else involved. Anyway, those are sort of 4 views. You might have a view somewhere in there. Well, I'm going to argue that it's number 3 here that's required. It is science, but it's something outside the science that we know today. And that's really my thesis here. And arguments, well, some of these I'll talk about. Arguments from philosophy, certainly from mathematics, I'll say something here, and from physics, and a bit also from biology. Not a great deal from psychology, but a little bit perhaps. So these subjects are certainly among the things which are relevant to this question. So let me move on. Well, I'll leave that there for a moment. And since I'm going to say that it's not computation, let's come back to our picture here, you see. If I take the view, not number 4, that there is something in the physical world that's responsible for our mentality, and if the physical world is governed by mathematics, and incidentally, I've drawn this picture rather deliberately as a paradox, because if each one of these things seems to come out from the one before, then there's something a little mysterious about that. So, if you like, there's another mystery, which is how the whole thing can fit together. But let's not worry about that for the moment. Let me just say what I mean by, if we thought that consciousness was a result of computation, let me indicate that in the diagram. Well, the first point I should make is that in mathematics, there are many things which lie outside computation. This is the kind of thing you get to know if you work in the field of mathematics. You may not often use these things, or you may, but there are certainly, and I've illustrated also in this picture, that whatever is computable is really a rather small part of mathematics as a whole. Now, it might be that the physical world, the actions of the physical world, are totally encompassed by the computable part of mathematics. Might be, well, there might be more to it. It might be that there's computable mathematics which extends beyond the scope of the physical world. But my thesis will be, if I say number 3 here, that somehow the scope of the computable does not include whatever it is that's responsible for mental activity. So that sort of indicates the point of view I'm trying to express here. Well, it doesn't say that it's outside known science, but I'll come to that. Okay, well, let's say something about why I think that we need something beyond, say, computation in understanding how the mind operates. Well, consciousness has many manifestations, and you can refer to passive things. That's qualia, that's our perceptions, if you like perceiving the color red or feeling pain or whatever it might be. And on the other end of the scale, active, that's usually described in terms of free will. If you use your consciousness in some way to influence what you do, then that's what we call free will. And there are many, many aspects of consciousness. I've listed a number of things there, none of which I'm really going to talk about. I'm going to concentrate instead on understanding. Now, understanding, it seems to me, is somewhere between passive and active. Now, I don't know what understanding means. So you might say, why am I going to talk about understanding? I don't know what it means. Well, I'm going to address the question of whether a computer or a computer-controlled robot could be capable of genuine understanding. And I'm going to describe, well, what I'm going to say about understanding is to relate it to 2 other things I don't know what they mean either. One of them is the word intelligence, I don't know what that means. Understanding, I don't know what that means. And awareness, well, that's really what I've been talking about. And I don't know what that means either. You might say, why am I standing up here talking about 3 things I don't know what they mean? Well, you see, that's one of the advantages about being a mathematician. You can talk about things that you don't know what they mean, as long as you can talk about the relationships between them. So all I'm really going to address here is that whatever intelligence is, it's something that requires understanding. That's when I say genuine intelligence. I think it would be unreasonable to say of an entity that it's genuinely intelligent if it doesn't possess any understanding at all. So I would say that intelligence requires understanding. Understanding is a prerequisite for intelligence. Likewise, although I don't know what awareness means, it seems to me it would be unreasonable to say of an entity that it understands something if it's not even aware of it. So I would say understanding requires awareness. So there are these implications, you see. It's really, this thing implies you need awareness for understanding, you need understanding for intelligence. So if understanding can be shown to be beyond computation, then intelligence is not a matter of computation. Moreover, certain aspects of awareness, and perhaps all of them, are beyond computation also. So I want to try and address the issue of understanding and try and argue that whatever it is, it's something which a computer doesn't do. And if you work with computers, it's in a sense how you feel about them anyway. I mean, they do things that they're told to do. They do them marvelously well. They can compute things and produce answers. But that answer is no use to you unless you understand what it means. What was the computation doing? What was it about? So, in a certain sense, the understanding is complementary to the computation. It seems to be something different. Nevertheless, if you believe that it's computations which control all our mental activities, then you would have to say understanding was, in some way, something that you could at least simulate computationally. Now, one of the most impressive things that have been achieved by artificial intelligence is building a chess machine that in a match against Garry Kasparov was able to win. I think it might have been a little lucky, but nevertheless, it did win. Shouldn't begrudge it there. But the question arises here, let me put this one over here. Does a computer, in particular, does Deep Blue, actually understand the game of chess? Well, here I have a position of chess. It's really a chess problem made up by, I believe, William Hartston, where the problem is white to play and draw. White is, of course, brown in this position here. And you might think, well, that brown has a considerable disadvantage because there are 2 black rooks extra and 1 extra black bishop, which would be absolutely overwhelming were it not for the fact that there is this barrier of pawns which simply blocks off the black pieces. There's no way that they can get across. But you give this position, I say it's easy for humans. You see, what does a human do? Just wander around here, make sure the barrier of pawns is left intact. There's no way you can lose. Easy for humans. But if you give this to essentially any chess-playing computer, in particular it was given to Deep Thought, which was Deep Blue's predecessor, it was also given to Deep Blue. And what does it do? It takes the rook with the pawn, opens up the barrier of pawns to achieve a hopelessly lost position. Well, the thing about this is not only can you see why that's a bad move, but you can see why the computer does it. Because what do these devices do? I should say not all of them, because some computers nowadays are programmed so that they can particularly make the right move in that position, or things like it. Of course, you could say, if you see that position, don't take the rook. But so you could certainly make your computer make the right move in that position. But in a sense, that's sort of begging the question. But you can see why, if you don't specifically program it to do something like that, why it's going to make that stupid move. Well, you see, what it does, basically, is to compute move after move after move after move after move after move to a certain depth, and then it has to assess whether the position is improved or not. And, well, you see, it takes a long time for the pieces to pour through the hole and checkmate the white king. And, in fact, it takes too long, even for Deep Blue. So it will, after a certain stage, simply tot up and see, oh, well, it's got a rook open more than it had before. It must have improved. See, so you can see why it does that. But does that mean that it understands the game? No matter how well it plays, you could argue that failing on a position like this is an indication that it doesn't understand chess. Let me give you another position. This is also due to it's due to William Hartston and David Norwood, and it was part of what's called a Turing test. The idea was that you have a number of human beings and a number of computers, and all you're allowed to know is their responses to questions. Well, in this case, the questions were to make the right move in various chess positions. And the problem, I should say half the problems were easy for human beings, like the one I just showed you, and half were easy for humans and hard for computers. The other half were the other way around, easy for computers and hard for human beings. And it was an extremely clean test. You could easily tell which were which. In this particular position, it's very like the one I just showed you, but you see, once your computer maybe has got used to the idea of barriers of pawns, you give it this one, there isn't a barrier of pawns, but of course what you do is you take this bishop and you place it there, pretend it's a pawn, roughly speaking, and you're back with the previous position. Whereas you give it to the computer, what it does is take the rook. Now these are of course very special positions that don't come up in a natural way in a game, but that's not the point of what I'm trying to say. I'm trying to say there is a distinction between what seems to be being done by pure computation and what a little bit of understanding can do. There does seem to be a difference. And the fact that this kind of test was made such a clean distinction does seem to indicate that there is a difference, at least with our present understanding of how to program computers and so on and so forth. Of course, it's not a completely conclusive test because, well, in particular, chess is a finite game. So even with absolutely brute force computation, you could make the right move in positions like this. Chess is a finite game. Of course, it's a long way beyond what could be done with present-day computers, but you could, in fact, imagine a computer which simply by brute force computation went right through to checkmate, and then it would certainly make the right moves. So that's a weakness with this kind of thing, to try and illustrate my point purely in terms of something like this, you can certainly argue, well, is it conclusive? Let me therefore turn to something where you get around this problem of finiteness and turn to mathematics. So my arguments really will be about mathematics. Don't worry, it's not going to be complicated mathematics. It'll be mathematics which is a little confusing, though. I'm going to be talking only about the simplest type of numbers in mathematics, what are called the natural numbers, but I'm including 0 here, 0, 1, 2, 3, 4, etc., the whole numbers which are not negative. Now, suppose you wanted to prove some statement or convince yourself of the truth of some statement which was a statement about all natural numbers. So it's not like the chess position, which is sort of finite, but where you're actually making a statement about an infinite number of things. Now, the kind of way you would prove some statement about an infinite number of things, well, there's a well-known procedure referred to as mathematical induction. Now, mathematical induction, if you want to prove that some property, which we'll call P of n, is true for all natural numbers n, so you're trying to prove all, P0, P1, P2, absolutely all of them, infinite number of things, what you can do is establish that it's true for 0, that's one finite thing you have to do, and show that if it's true for n, then it's true for n plus 1. And this is just, each of these might be a finite calculation, and then you will have established an infinite number of things. So it's a very powerful procedure. It enables you to do an infinite number of things by only doing 2 things. So that's pretty good. That's the kind of thing you like to do in mathematics, of course. Well, if you include the ordinary rules of arithmetic or something, it's what's called piano arithmetic, first order. I'll come back to that point later, but don't worry about that. That's just for the logicians in the audience, if there are any. Now, the question I want to raise is, are computational rules, such as those provided by ordinary mathematical induction, like these ones here, sufficient for establishing the truths of arithmetic? Well, there's a famous theorem known as Gödel's theorem, which simply says no. So no matter what rules you have, if you accept them as only giving you true things, if you've already accepted those rules, Gödel says, nope, that's not enough. You need something else. Now, I've also put the word perceivable there a little faintly, so I'm not sure whether you can read it, a little deliberately perhaps, because it's also addressing a slightly more extended statement. That is, are those truths which are perceivable by human beings in principle, are the computational rules sufficient for them? Well, by sort of extension of the argument, you can treat these things as well, but I don't really want to go into the details of all this. In fact, even though I could really prove this Gödel statement, not too hard, it's not too hard to show, and I could certainly do it here. I'm not going to do it here. I'd rather do something else, which is give you an example. And this, well, actually, before doing that, let me put this over here so you can see what it says here. Before giving you an example, let me tell you what Gödel's theorem a little bit more precisely says. It says that the perception of mathematical truth cannot be reduced to a set of mechanical rules. And a little more precisely than that, what it says is that for any set of mechanical theorem-proving rules, which we call R, we can construct a mathematical statement, which I call G of R, which if we believe in the validity of R, we must accept as true. Yet G of R cannot be proved using the rules R alone. So if you're using rules like these here, which you're prepared to accept, you think, okay, anything which is derived by means of these rules must be okay. If you've got to that stage, then what Gödel shows, okay, here's a statement which you must also accept, and he shows you why you must accept it, then, but nevertheless, it's not accessible by means of these rules. So somehow you can always, if you've got the rules and if you accept them, he shows you how to transcend those rules. So you can always step outside whatever limited rule-following scheme you had before. The trouble mainly with this kind of thing is that given rules, it's a very complicated statement. This G of R would be something that nobody would really be interested in were it not for the fact that it happens to have this property. So let me do something else, which is to give you an example. And it has the advantage of being something that you can explain to people, even if they don't know much mathematics at all. All you have to know is how to write numbers down and things like that. And it's a theorem due to Goodstein. In America I should call him Goodstein, shouldn't I? Proved in 1944. And it is, well, let me illustrate it by an example. And what you have to do is you take a natural number, for example, this is just an illustration, 1077. And then what you do is you write it in a binary form, well, in effect, so you use ones and zeros. People are familiar with these things nowadays, but what that means is that I'm writing it as a sum of powers of 2. So this one here means 2 to the 0, that's 1. Whenever you see a 0, it means the power of 2 that's missing. Whenever you see a 1, it's a power of 2 that's present. So any number, any natural number, can be expressed as a sum of distinct powers of 2. And here we have 1077 represented as 2 to the 10th, plus 2 to the 5th, plus 2 to the 4th, plus 2 squared, plus 1. That's 1024 plus 32 plus 16 plus 4 plus 1. Any number you can write like that. Any natural number, positive natural number. Now you see, you might say, well, look at those numbers up at the top there, the 10 and the 5 and so on. I haven't written them in this way, as powers of 2. Why not do that? So what's 10? Well, 10 is 8 plus 2, that's 2 cubed plus 2. 5 is 2 squared plus 1. 4 is 2 squared, and so on. So you can write all the exponents also in this way in terms of powers of 2. But then you say, well, look, you're not really finished. What about that 3 up there? Well, okay, 3 is 2 plus 1, and now I'm finished. I'm finished writing it in terms of powers of 2. I could have chosen a bigger number here, and I might have had to go to higher powers than the ones that I had here. But I think you can see that whatever number I start with, I will always be able to write it in some such way where the exponents go up and up and up, but at a certain point I come to an end, and they're always written, everything's written in terms of powers of 2. Now I'm going to describe 2 operations that I'm going to apply to this number. The first one is to increase the base. When I say base, I just mean the 2's here. Increase the base by 1. So the 2's go up to 3. That's what I'm calling operation A. And then this number becomes 3 to the 3 to the 3 plus 1 plus 3 plus 3 to the 3 plus 1, etc., etc., etc. Okay. It's much, much bigger than it was before. Operation B is subtract 1. That's pretty easy. You just take the 1 off the end, and there you have that number. And you're going to alternate A, B, A, B, A, B, and see what happens. So A means you take all the 3's and replace them by 1 more, that's 4's. And I get 4 to the 4 to the 4 plus 1 plus 4 plus 4 to the 4 to the 4 plus 1, etc. And then I subtract 1. Well, it's not quite so easy now because there's a sort of handy 1 sitting at the end there. But if you know how to take 1 from 10,000, you know what to do. That is to say, you see you've got the 4 to the 4, 1 off means 3 times 4 cubed plus 3 times 4 squared plus 3 times, etc. It's only 1 smaller, after all. Now I replace all the 4's by 5's, and you leave these 3's, these are just coefficients, you just leave them alone, but the 4's in the expression go up to 5's, and I have a new number, and I just keep doing that again and again and again. And the question is, what happens? Well, I give you a feeling for this. I started with 1077. The green ones were something like 10 to the 40. The purple ones about 10 to the 600. The brown ones about 10 to the 10,000. And they're going to go up and up and up and up and up and up until they reach 0. That's Goodstein's theorem. Whatever number you start with, they will always, applying this rule A, B, A, B, end up with 0. That's pretty surprising. Moreover, there's no way you could prove this by mathematical induction. It's a Gödel theorem for these rules here. It's a remarkable thing. And it's true. I tell you, really, you do only end up with 0. But what I'm going to do is to give you a proof. I'll give you a proof first that the mathematicians who know the right thing in the audience will see at once that it's a proof. Okay? And then I'm going to try and persuade the rest of you, at least can sort of give you a feeling for why it's true. Okay? Now, how does the proof go? You imagine this written down on some enormous okay, incredibly enormous piece of paper, and what I'm going to do is simply block off all the bases all the way down. I just put a splodge over them, okay? Now, operation A doesn't do anything at all, because you can't even see the base underneath the splodge, whereas operation B, in a certain sense, makes it smaller. And the sense can be made precise if you know, now here's where the mathematics comes in, if you know what an ordinal number is. And if you know these things, the splodge stands for Cantor's smallest infinite ordinal number, which is called omega, and the procedure, operation A does nothing, the operation B gives you what's called a descending chain, and it's one of the fundamental theorems of ordinal arithmetic that any descending chain of them always has a least member which can only be, in this context, 0. So there's the proof. Of course, I'm not saying that many people may not know what ordinal numbers are or what transfinite induction is, which is what I've just given you here. So let me just give you a feeling for why it works. Just a feeling. You see, here we have these towers. You have a really big one over here, a slightly smaller one as you go. And each time you subtract the 1, okay, it chips away, eats up what number you have here, and then it eats into the next tower. And that tower tumbles down, produces a whole lot of junk at the end, and then you eat that away, eat that away, eat that away, and then you eat the next tower. And it always produces something in a sense smaller than you had before. And this goes on until you reach the big one. That tower starts tumbling down, produces smaller towers, and you eat them up, and so on, and you end up with 0. I would recommend, as a little exercise, well, first of all, try it with 3. That's easy. 3 comes to 0 pretty quickly. Then try it with 4. That's the test. Try it with 4. You'll be surprised how big the number gets before it goes down to 0. But once you convince yourself with 4 that it works, it's not so hard to believe that it always does work. And it's really just a question of understanding. Okay, I mentioned transfinite numbers and all that, but that's just a sort of sophisticated way of incorporating a certain kind of understanding. Well, Paris and Kirby proved this in 1982. Well, I should say Goodstein proved the theorem, but Paris and Kirby showed that there is no way of proving this theorem using mathematical induction. It is an example of a Gödel theorem for mathematical induction. It's one of these things here. So G of R, if R were the rules that I gave you, induction together with the rules of logic and arithmetic, that's what piano arithmetic is, first order. This is a Gödel theorem for, this is the Gödel theorem for that. Well, okay, so you've seen the Gödel theorem. Now, what's sort of going on? In fact, how did Paris and Kirby prove that you can't do this by mathematical induction? Well, the sort of way you do that kind of thing is to construct a sort of number system, which you might call supernatural numbers, or Douglas Hofstadter in his book coined a term, supernatural numbers. It's quite a nice term. I think I've got it somewhere on the slide. Yes, there we are. Just some funny kind of number, which is obviously not natural number, but for which the rules of mathematical induction do hold, but for which the Goodstein theorem is false. And you just have to show that. Okay, it may not be so easy, but once you've shown that, then you've shown it's not a consequence. But another way, then, of expressing what the Gödel theorem is sort of saying is that there is no way of characterizing the natural numbers by means of rules, by a finite set of rules. So you might say, well, how do we know what the natural numbers are? How do we know it's not one of these funny systems? But we know what the natural numbers are. Not only do we know, but a child knows what the natural numbers are. And it seems to me this, in a certain sense, is carrying the gist of what I'm trying to say here. And coming back to the transparency I had to begin with, well, let me go to how you teach a child. I think this is sort of Sesame Street or something. How do you teach a child what is meant by these numbers? Well, you just show them a few examples, and here I've had some oranges and apples and bananas and things, and you just show them a number of examples. And after a little while, the child gets the idea and says, oh, I know what they are. I know what you're getting at. That's what 4 is. 4 is the thing which you're expressing with this, what's common between these things here. But if you try to teach a child, giving an axiom system or something, it's obviously a stupid way of doing it, but what I'm saying is not only is it a stupid way of doing it, but you can't do it. There's no way simply giving formal rules of expressing what the natural numbers actually are, just giving formal rules. Nevertheless, you can somehow get the idea, and what I would argue is that it requires consciousness. It requires the awareness of the child somehow. The realization of what a number is somehow a manifestation of consciousness. And when I talk about this as a mystery here, that's really what's sort of going on. I've used the terminology here, which I find some of my friends or perhaps enemies object to. It's a very Platonic way of talking about things, to say this is an example of contact with the Platonic world. If you work in mathematics, you somehow get the feeling that there's worlds out there quite independent of us. It's not something which really emerges out of our mentality, but it's something out there which we somehow access and reach in some way. It's just a way of talking, if you like, but that's the way I find it's quite useful to express what's going on here. The understanding of what a natural number is some realization. Sometimes people say an aha experience or something. It's some kind of realization of what is really going on, what a natural number is in some sense. But you don't do it by telling all the rules. And I don't say you can't do that, because that's what Gödel says. Okay, so that's telling us, as I'm arguing that it's telling us, that mentality, well, it's not quite this picture, I suppose, but that mentality somehow is not encompassed by rules. Well, it is saying that, I suppose. If you believe that mentality is a product, in a sense, of physicality, then it would tell us that we're outside computation. Well, there are actually loopholes to this argument, and some people, certainly if you believe strongly in strong AI, you would try to find weaknesses in this kind of argument, and certainly people do. So I'm not going to try and say that what I've said so far is conclusive. I wrote a whole book on this to try and explain. I'm not going to go through the arguments here, and what's rather disconcerting is that a lot of the people who complain about the book haven't gone through them either, I see. So never mind. I would recommend, perhaps rather than looking at the book, looking perhaps at this website thing here. So let me put that there. It's awfully long. I'm not going to, if anybody wants to take it down, it's something you can find. A thing called Psyche. There were a lot of reviews of Shadows of the Mind, this is the book here, and I tried to reply to them. So I'm really telling you should read my bit, but if you want to read the others too, that's fine. Okay, but for these purposes of this lecture, let's say, okay, let's accept what I'm saying, and that's telling us that mathematical understanding is not computation. There's something outside pure computation, rule following, you see, if you like. It could be more precise about what I mean by computation, but basically it means something which you could put on a computer. And, of course, one of the arguments people might make is whether what you put on a computer is rule following or something like that. But let's not go into those arguments. Let's just accept the argument for the moment and say that what I've argued for is that mathematical understanding is not something you can reduce to computation. Now, of course, that doesn't tell us everything is non-computational in our mentality, but it does seem to me unreasonable to draw a line between mathematical understanding and human understanding generally. In fact, when I was describing how you might prove the Goodstein theorem, I was telling you in terms of towers falling and that sort of thing, and that's really not so different from other kinds of understanding. It seems to me to be quite unreasonable to draw a line here, which is rather curious, because sometimes people accuse me of saying that, there's something, mathematicians have a wonderful way of perceiving what's going on here that's not accessible to anybody else. I'm certainly not saying that. I'm saying that understanding, all kinds of understanding, are really the same thing. Mathematics is, well, okay, it's more kind of rigorous, it's more refined, more abstract. That's what makes it hard sometimes for people. But there's nothing really different here. But I don't want to draw a line either between human understanding and human consciousness generally. Of course, there are lots of other things in consciousness than understanding. For example, perceiving the color red. But I think you might agree that it's much more likely, a priori, that, well, mathematical understanding, certainly you might think, was much more likely to be something computational than what perceiving redness is. So it seems to me unreasonable to draw the line here. So, okay, that would argue, well, that's not a proof, it's arguing that all these things are outside computation. Now, I would argue that it's not reasonable to draw a line between human consciousness and animal consciousness. It seems to me that there are quite enough similarities between the way at least some animals seem to behave. Anybody who's owned a dog will feel there's somebody there, and so on. And there are many anecdotal examples of how animals behave, which seem to me indicate very strongly that they also have consciousness, have awareness. So I wouldn't like to draw a line anywhere here. It seems to me that, well, that non-computability in some aspect of consciousness, for example, mathematical understanding, strongly suggests that non-computability should be a feature of all consciousness. And that's really what's kind of strange about consciousness, is that it's involving something which is non-computable in some sense. That would be my position anyway. And if you believe, as I do, that we should not look outside the actions of physical world, then this implies that there is something outside computation. If I can find that little bit of the transparency. Yeah, here we are. That there is something outside computation in physical activity, and indeed the part which is responsible for our consciousness is outside that, so that the picture would be something like here. So that's my position, but I think I really need to clarify what's meant by non-computable, because it's not a notion which is familiar to people if they haven't seen these things before. So let me try and say what I mean by referring to a toy model. It's the kind of thing that people in this institute would do a lot of, I imagine. Certainly it's very common and a good thing to do. I'm not complaining about it. To form a model universe, which is admittedly not meant to be how the actual universe works, but it's something which illustrates a point. So this particular model I'm going to show you is by no means how I think the world operates, so don't get me wrong on that one, but it illustrates a point. Now in this model, it has a discrete time, which goes 0, 1, 2, 3, 4, like that, and the state of the universe at any one time is to be given by a pair of polyomino sets. Well, I have to say what a polyomino is. A polyomino is a set of squares in the plane glued together along edges, such as this cross here or that shape there. And the question I'm going to address is whether or not you can cover the plane using that shape or set of shapes and nothing else. So you can see with this cross, essentially as I've indicated here, that you can cover the plane with it without gaps or overlaps. With this shape here, again made out of squares joined together, equal squares joined together along the edges, a polyomino, and again you can cover the plane with it without gaps or overlaps. It will tile the plane, as you say. Now here I have two shapes, neither of which will tile the plane. If you try with that one, you find a gap will appear somewhere, no matter how you do it. With this one, a gap will appear somewhere. But if I use both shapes at once as my set, then indeed it's possible to tile the plane with that set. Here I have another shape, which not so easy to see perhaps, but indeed it will tile the plane, and you can see if you can see how that works. Okay, those are polyominoes, and that's what I'm interested in whether they'll tile the plane or not. What about this universe? Well, I'm talking about sets of polyominoes, so here we have two of them, say, finite sets, and I imagine listing them somehow, all possible sets in some computational way. That can be done. I'm not going to try and say how that would be done in practice. I've only sort of made the numbers up here, but never mind. You have all the possible sets of polyominoes listed in some way, in some computational way, starting with the empty set with no tiles in it at all. And the dynamics, how this universe operates, so there are two of these sets you have at any one moment, and the universe goes like in the following way. We start with two of these ones, and two empty sets, and it's a sort of inductive procedure. If the state at any one moment is SP, SQ at time t, then at the next moment in time, t plus 1, you look to see if SP will tile the plane. Is it one of these? Say, will it tile the plane? If it will, you simply go on to the next one on the list here. SP plus 1 SQ. If it will not tile the plane, you still go to the next one on the list, but you swap the two over. And that's all it is. That's the universe. The evolution process, something like this, as I've indicated. The evolution is deterministic. It is absolutely clear what the universe does at next stage. If you notice at one time, it's a completely deterministic rule about how it evolves, but it is not computable. That depends on a theorem due to Robert Berger. He showed, in effect, that what's called the tiling problem is undecidable computationally. That is, the little tricky thing here, you've got to decide whether they will tile the plane or not. Although it's certainly true that it either will tile the plane or it will not tile the plane. So whichever way around it is, there will be a unique evolution of this universe. But there's no computer program which will tell you always which is the right thing to do. And that's what Robert Berger proved. Slightly different from that, but you can deduce it from his theorem. And the theorem of Robert Berger depends upon the existence of certain tile sets, like, in fact, this one here, which I'll just show you. There we are. The way it tiles the plane, well, I haven't done the whole plane, of course, but I've done a reasonable part of it here. And those three tiles will tile the plane. Take it from me. See if you can see how that works. If you like, I'll tell you how it's done at the end. But the point about it is that even though it will tile the plane, it will not tile the plane with repetition. It never repeats. The tiling pattern never repeats itself. It's always different as you go out. And the Berger theorem depends upon the existence of tile sets like that. Now, I won't go into it any more than that, but it's a mathematical theorem, and the point about this model is not that our own universe is in any detailed way like that, but maybe it's like that in a certain principle, according to this. But you see, it might even be deterministic. I'm not saying our universe is deterministic, but it could be, and it could be deterministic, but still not computable. And this is sort of a new question. I mean, philosophers over centuries have argued about whether the universe is deterministic. But what I'm saying is that something else you can ask about the universe is whether it's computable or not. And that's a different question. That's all really I wanted to illustrate with this model. But what we're really interested in, of course, is not that model, but the actual physical world. Now, are the laws of physics computable? Well, we don't know all the laws of physics yet, but the way we do physics is illustrated on this transparency here. Well, of course, I've left all the equations off, but the point I'm trying to make here is that when we do physics in practice, we do one of two things, basically. We do quantum physics or we do classical physics. And roughly speaking, quantum physics is about small things. It's about atoms, molecules, and so on. Small is a little, you have to worry a bit about that because they can stretch over large distances, quantum effects. I'll come to that in a moment. But they're small in the sense of that the amount of movement in material is small. Whereas if you have big things, then you use classical physics. I mean, in practice you do. And they seem to be quite different. Well, here I have Newton's, Maxwell's, Einstein's laws for classical physics. Maxwell's about electromagnetic fields and light. Einstein about things when gravitational fields get large or velocities are large. But if you're talking about small things, then you do use a different set of equations, the Schrödinger equation, or something equivalent. Now I've used the word C for the classical level and U for what's called unitary evolution. That's, roughly speaking, what the Schrödinger equation does. And if you have something which stays down at this level, well, you say, I've used these words, which are the same words I've used there. Deterministic. And people might worry, surely quantum mechanics isn't deterministic, is it? Well, it is if you stay down at one level. It's not deterministic if you do what's called making a measurement. And a good illustration of a measurement would be a Geiger counter, which clicks if it receives a quantum particle, and that's something which goes from here to here. That's to say, it magnifies, if you like, a quantum event up to the classical level. And when you treat this mathematically, you do something quite different. Now, I'm not going to enter into all the arguments here, of which there are many, I should say, but let me just leave that up here and tell you, if you're not familiar with these things, roughly speaking, what U and R are. Well, this is the trouble here is I have to give you an entire lecture on quantum mechanics in I think, probably half a minute by now. But let me just give you at least all we want to know here about quantum mechanics. And it's fairly well illustrated by the two-slit experiment. Here I have a source of quantum particles, let's call them photons, two slits and a screen at the back. And if one slit happened to be closed, the other open, then you would find certain places the particle could reach. Let's single out a particular point here. If you close that slit, open the other one, it maybe you could still find it could reach that point. But if I've chosen this point carefully and open both slits, I may find that somehow it now can't reach that spot. So somehow the two alternative things which the photon might do mysteriously cancel each other out, and when both slits are open, you find suddenly it can't do it. Very strange. But that's the way quantum mechanics works. And the way we try and understand it is by considering that somehow between here and here, the two things that the photon might do, in some sense, coexist. You say there's a sort of quantum superposition of one thing and the other. And here I've got alternative A, coming from this source, going through the top slit and reaching that spot. Alternative B, going through the bottom slit and reaching that spot. And you have to consider that in the process between here and here, both things, in a certain sense, are felt out together. And you have a weighting factor, which I call W here, and I guess in America I should call Z. That weighting factor, you might think, was a probability weighting of one thing or the other. Not at all. It's not a probability weighting because these are complex numbers involving the square root of -1. Okay, that's what you do. I mean, what do you make sense of that? Well, that's what we have to do. We do that all the time now. Certainly in this institute, do this kind of thing. Get used to it after a while. And the operation of the U procedure, the Schrödinger equation, if you like, it has the one property that I want to emphasize here. It's what's called linear. That means that if you just had A, whatever it did, according to the Schrödinger equation, well, it does something. Whatever B does, it does something. What this linearity says is that if you had WA plus Z times B, then it would do W times whatever A does plus Z times whatever B does. Somehow each one goes its merry way without worrying about whether the other one is there or not. And you might say, what's the point? Well, you need the other procedure here, which you bring in when you somehow magnify from one level to the other. Magnify to the classical level, you completely change the rules. You now take these two complex numbers, I've represented them here on the complex plane, and I look at the distance to the origin, that's what's called the modulus of the complex number. I take the square of each, and the square of the modulus of each of these, the ratio of the two, gives us the ratio of the probabilities of the two alternatives. So suddenly they become probabilities. But they only become probabilities when you go from here to here. When you're down here, that doesn't work. You've got to keep the two things running their own happy way with the complex numbers. They've got to be the complex numbers. And only when you make the measurement, suddenly you change the rules, and they become probabilities. Okay, that's the way it works. Don't blame me. Blame the universe, I suppose, because that's the way it works. Now, I want to tell you two things about quantum mechanics. One is a very curious thing. It's sometimes called non-locality, more correctly called entanglement, I suppose. And, well, I'll put the whole transparency there. It's what's called an Einstein-Podolsky-Rosen effect. It's telling you that although quantum mechanics is to do with small things, it's not to do with small distances. And there's an experiment here which was done by Alain Aspect, which illustrates this general kind of Einstein-Podolsky-Rosen effect, which I won't try and explain in detail, but let me just talk about the experiment. In this experiment, there's a source of pairs of photons, which go off to opposite sides of the room, distance of something like 12 meters apart, and there are detectors, a pair of them here, and a little switch, which tells you one or the other of the detector is going to measure one thing or another thing. They measure different things. But the decision as to which one is going to do the measurement isn't made until the photons are in full flight. And the gist of the whole thing is, according to a theorem, a wonderful theorem due to John Bell, is that the predictions of quantum mechanics cannot be explained by these two photons being separate, independent, non-communicating entities. They can't be two things separate, each doing its own thing, not worrying about the other one, out of communication. There's no way you can explain the predictions of quantum mechanics without them being, in some sense, one thing. It's what's called one entangled state. And the experiments, I should say, do confirm quantum mechanics, and they show that, indeed, pairs of photons have to behave as single entities. And it's one of the most striking features of quantum mechanics. Very well confirmed now. Not just 12 meters. I believe that now experiments of this nature are done over a distance of something like kilometers. I suppose I have to translate that into miles, but never mind. Kilometers, you know what that is. Okay, that's an amazing thing about quantum mechanics. Now I'm going to tell you something else about quantum mechanics. Also amazing, but, well, we'll see. That's poor old Schrodinger's cat. In fact, some of you might have been at my lecture yesterday, and I talked a lot about Schrodinger's cat then. I'm using the same transparency here. But the point about this is that if you follow the rules, the U rules, and you regard these two alternatives, the two alternatives here are a quantum particle, say a photon coming through, split into two roots. It might go this way, it might go this way, but you have to consider that indeed it's not one or the other, it's the superposition of the two, otherwise you get wrong answers for other things. So it's got to be the two things happen in superposition. This one goes, fires a gun, kills the cat. The other one goes off, the cat remains alive. But because of the linearity of quantum mechanics, whatever A might do or whatever B might do, the thing I was just saying before, if both happen at once, that's the two things, photon going off both ways, then you have to consider that indeed, if you're following U, that both things take place. The cat is alive and dead at the same time. And Schrödinger brought this example to people's attention. Not that he ever did it, of course. He wouldn't have done such a thing. I was told he didn't like cats, but I'm sure he was a very humane person. He would never have done such an experiment. But it's a thought experiment. It's a thought cat there. The idea is just to show, and what Schrödinger was basically saying, is saying, don't believe my equation as applied to cats. But nowadays, I think people tend to believe Schrödinger's equation more than they believe Schrödinger. But basically, what it's telling you is that you can't consider the U level at all as applying at all scales. Okay, it's a big argument, and all sorts of people will come up and present different viewpoints and so on. I'm just going to present you with my viewpoint. My viewpoint is this, that we need a new theory. But there's a new theory which all these other things are approximations to, the quantum level, the classical level, something which is not linear, which somehow generalizes the procedures of U, quantum mechanics, the linearity of the Schrödinger equation, non-linearities, which will lead to some kinds of instabilities which look approximately like what we do, but aren't what we do, if we could find the right experiments. Okay, now, the point I want to make, though, about this, because what's this got to do with the rest of my talk? You see, I've got them drifting off, you might think, on a tangent. Well, I've been talking about what laws physical world seems to operate according to, and I've been trying to say that if we want to understand mentality, we have to understand how there can be, in the operation of the physical world, something which is outside computation, so something which is beyond the scope of the computable part of mathematics. That's what I'm trying to say. But how do we understand the physics, and what about the physics we understand today? Well, the physics we understand today has basically these words attached to it, if you like. The classical level is computable. Well, people compute it all the time. Actually, there's a bit of a question mark here, because the normal notions of computability apply to discreteness, whereas the rules we use in classical mechanics use continuous parameters. So there's a question mark. So I don't want to say it's absolutely clear-cut here. there are various theorems, and I'm not quite sure how well they cope with the general continuous situation. But let's say computable. It seems a plausible statement anyway. Likewise, quantum level, well, it's a little bit more persuasive that it's computable here because we actually have linear equations, and those are easier to handle. And the measurement process, as we use it, is completely random. You magnify quantum events at classical level, and the procedure R, measurement process, reduction of the state vector, is a purely random process. So, okay, we might have something which is like a computer here, something like a computer here. We have to incorporate the randomness, but a computer with a random element doesn't really get you anything more than without the random element. That's another point of subtlety, which I don't want to stress here, but I think in practice, people always incorporate random elements, or very often do, by something which is called pseudo-random procedures, and to all intents and purposes, it's just as good. So it's a bit hard to see that randomness itself is going to get you anywhere that you couldn't really have got with computability. So that's the argument is that it's not in this picture. The non-computable is not in this picture. So what I'm trying to say is that it must be in this part of the picture. Now, I should say that's a weak argument. It's the Sherlock Holmes argument, saying if once you've eliminated all the things which are impossible, whatever is left, no matter how improbable, must be the truth. And I'm using that argument, which I admit is not the strongest of arguments, but nevertheless, as long as you're rigorous all the way through, it's still a good argument. So what I'm trying to say is this new theory, which I'm calling objective reduction. The OR is a nice acronym because it stands for or. The cat is dead or alive. But we don't know the theory. That's the trouble. Well, I said originally that, okay, it's not outside science, but it's outside, I would claim, existing known science. So this is illustrating what I'm trying to say here. The extended physical worldview is one which incorporates the correct theory that I maintain we need here. Now, I just want to finish. I see I've run myself rather out of time. I want to give you at least some feeling for what the nature of this theory should be. I don't know the theory, so I'm not going to tell you what it is because I don't know it. I can't tell you. I wish I could. But I'm going to tell you the sort of theory I think it is and the level at which I think it comes in. And again, I'm afraid I'm using a transparency from yesterday. But you see here, I've replaced the cat by just a lump of material. Okay, that gets rid of a lot of problems. You might worry about whether the cat was conscious and so on, which I would argue it is, of course, from things I've just been saying. So that makes life more complicated. Let's replace it by just a lump of material, which, if the photon goes this way, gets moved from here to here. If it goes the other way, it's left in the same place. And we have a superposition of two different lump positions, which if you try to draw it as a space-time diagram, space going this way, time that way, the curvature, according to Einstein's theory of space-time, due to the presence of the lump, is illustrated by this little bump here. As you move one over and leave the other alone, you realize you've got to superimpose not just two lump positions, particle positions or something, but two actual space-times. And I would argue that that introduces an essential uncertainty into an energy of the state, which is related, I claim, to a time scale, which you can compute by a certain formula. This is Planck's constant over 2 pi, the E.g. I'll give you two transparencies which say the same thing. Maybe I don't know whether that helps any, but perhaps it's a little clearer. The E.g. there, which can be described as how much energy it would cost you to pull a lump in that position away from another lump in that position to their locations, the separated locations. If you just consider gravity, so how much gravitational energy would that cost? How much pulling against the gravitational attraction would that be? Not much, very tiny energy, but you put it in this formula, in the denominator, you work out this time, and that, I claim, is a time for the superposition actually to decay into one or the other. So I'm saying that there is some kind of a nonlinearity, which says that it's not just this thing here and this thing here doing its own thing independent of the other, but there's some kind of nonlinearity which says that after a certain time scale, which you can compute by this formula, it goes into one or the other. Okay, we don't know that theory in detail. There are experiments which I suggested yesterday, I won't go into that now unless anybody asks me about them, which might be able to tell us whether this is right or not. But the remaining things that I want to say here depend upon it being right. So if it turns out wrong by any of these experiments, you can forget the rest of the things I want to say here. But let me say them anyway, because the experiment hasn't been done and it certainly hasn't turned out wrong yet. So what I want to do is to return to my initial question here, which is addressing what it is that's involved in mentality. I mean, what do we need here? What kind of physical structures, what kind of things do we need here in order to have mentality? Well, the only kind of mentality we know about is the mentality in human brains. And what's a human brain like? Well, it's a bit like that with a lot more neurons than I've drawn there. But these are a couple of neurons. And the sort of picture one has, and one of the reasons that people like to think that maybe brains are computers in some sense, is there is a great similarity between sort of transistors and wires and things, and neurons and well, axons and so on and so forth, dendrites. And you have a signal going along here, which then triggers another signal on the next one. And whether it does or not depends on the kind of synapse involved and so on. And it's very like a computer, at least at this level of discussion. And if that's all there were to it, I would have to admit it was like a computer. But there is a lot more to cells than simply the fact that they conduct, well, not actually currents, but signals, say, in the way that you might imagine with a computer. And it means that we have to look a little bit more closely into the structure of the cells. And here I've magnified up the synapse, that's the connection between one neuron and the next. And what one has is, well, there are these neurotransmitter chemicals which go across and transmit the signal from one thing to the next. But I've tried to look a little bit inside the cell to these structures referred to as the cytoskeleton of the cell, in particular little tubes known as microtubules. Now I've tried to magnify up a microtubule here. It's made up out of these proteins. They're known as dimers because they consist of two little pieces here. And they, well, the whole thing is made up out of these things called tubulin, these dimers. And, well, let me show you another picture of a microtubule. Perhaps I'll put this one over here. And I've just drawn it basically a little bit more clearly. They're very kind of organized structures, a bit like crystals almost. And according to a procedure known as, well, I'll call it the Hameroff process, Stuart Hameroff suggested that microtubules might actually send signals at a much deeper level than the signals that are involved in axon and dendrite transmission, that there might be signals going along these microtubules. And so the picture he had was that these little tubulin proteins, I just indicate how big they are here. They're sort of 8 nanometers this way by 4 by 4. And on his view, the little tubulin proteins could do one of two things. They're sort of what are called two conformational states. And there would be an electron in the middle here which goes from one place to another, and that causes the ones in the neighbors to do one thing or another. And you have something a bit like what's called a cellular automaton, sends complicated signals along the microtubules. Now, various people have looked at this kind of process theoretically later to see whether it's plausible, and a man by the name of Tulchinski came to the conclusion that it would only work if microtubules were what he called A-lattice microtubules as opposed to B-lattice microtubules. In my book, The Shadows of the Mind, I only knew about A-lattice ones, and the picture that I have here is actually an A-lattice. It's much more symmetrical. The B-lattice one has a kind of seam which goes down it, and the things keep falling to pieces and coming together again and so on. And it turns out that only the A-lattice would be useful for this kind of processing. We don't know for sure that it takes place, but if it does, it seems it has to be an A-lattice. So one of the ideas would be, well, you see, Stuart Hameroff's idea is that consciousness has to do with the activities of these microtubules. Now, in order to make contact with the things I've been saying, it would have to be not just something like Hameroff's process in the A-lattice microtubules, but it would have to be something where these quantum superpositions are involved as well. So we have to imagine that maybe it's something like what's called a quantum computer. You have quantum superpositions of these things. But I would say you need more than that, because you need to go beyond quantum mechanics. You need actually, if my arguments are correct, one needs not just something going along at the quantum level and some other things at the classical level. You need the new theory. So you need somewhere the superpositions to reduce into one or the other according to a non-computational scheme. So that's the idea. Okay, you could say that's very speculative. Indeed, I don't deny that. And I would argue that probably you need other structures than microtubules. There are a lot of interesting structures hanging around in synapses. And for example, there are these things known as clathorines. I like them particularly because they have this very nice symmetry. They're a bit like these things called buckyballs or fullerenes made of carbon, which have the same kind of structure, like soccer ball. These things are proteins. They're not the same substance at all, but they have the same kind of symmetry. And there is something rather conducive to quantum activities on a large scale is what you need by having symmetrical structures. And it so happens that these things hang around in the synapses. And they're supposed to be involved with transporting the neurotransmitter chemicals. Exactly what they're doing, I don't have a real suggestion. But it seems to me quite possible that there might be some large-scale kind of quantum activity going on which involves these things and microtubules and maybe all sorts of other structures as well. The kind of thing you should keep in mind for this is something like a superconductor. Superconductors were known originally as things only existing at very low temperatures, nearly absolute zero. Nowadays, we know of things known as high-temperature superconductors. These are large-scale quantum activities spreading over large areas. And remember the Einstein-Podolsky-Rosen things, where quantum effects aren't simply localized. They can stretch across great distances. So the argument would be that over large regions of the brain, you have some kind of quantum coherent activity, something like a superconductor. Okay, it wouldn't be any good if it needed absolute zero, but more recently people have started to see superconductors at temperatures, well, not body temperature, but sort of halfway there. So what one would need is something of that general nature, maybe not a superconductor, but something of that general nature, which would be involved in microtubules, maybe structures like this, over large regions of the brain. And we have a picture which I just sort of indicated there. I'm not going to explain it, but it's just microtubules with activities going on, and every now and again, a whole lot of them at once would reduce down, and in the process of doing that, would influence the strength of synapses. You see here, we have them here. The microtubules would suddenly all go and do one thing, and this would slightly influence the strength of synapses over large regions of the brain, and in that process, one would be taking advantage of what I'm saying, this process here. But you need not just quantum activity, not just classical activity, not just things going by the ordinary procedure from one end to the other, but where they're actually making use of this new theory. So it would need to be carefully integrated with some structures to do with how neurons operate as well, and so on. And of course, that's way beyond anything I would know how to deal with, but that's the general idea. And just to return here, well, just to summarize, I've argued originally that we need something non-computational involved in our mentality, and that non-computational aspect of the world therefore has to be in the physical world, if you believe that mentality comes about from physicality, and that's somehow how this thing all fits together. Okay, well, I think I'd better stop there. Thank you very much. Sure.
Rogers would be delighted to take the questions, and I'm sure there are questions.
Yes, I think it's pretty. Yes.
I'm curious about the meaning of computation. Let me suggest that mathematics was invented to address problems that humans didn't experience firsthand. And what I mean by that is, for instance, take a dynamic thing of a baseball player catching a fly ball.
Yep. Mm-hmm.
Or a leopard running down a deer in the plains. And they're very familiar with doing that as a bird is flying. Okay, and you can see that evolving over millions of years. And it's hard to deny that each one isn't unique. That is, each event that happens doesn't have to be computed somehow through some process in the brain. It's quite amazing when you see how accurate
sure.
But taking the best example of quantum physics, where until this century nobody even heard of it, understood it, or was even aware of it, how can our brain deal with this problem yet in the same way that we could catch a fly ball? And I'm proposing that we invented computation in the mathematical sense because it seems handy to address these problems that we're really not familiar with. And I'd like your feeling about that.
But I mean, mathematics has been going on a long time before quantum mechanics. I mean, the ancient Greeks and even before them, the Babylonians and so on, certainly developed mathematical ideas. And we didn't need quantum mechanics to think mathematically. And in fact, although the very notion of computability is a modern one in the sense that Turing and Gödel and Post and Church and people only came upon this idea in the 1930s, essentially. But I would regard it as accidental that is more or less contemporary with quantum mechanics. I don't think there's any direct connection in our understanding there. The basic ideas were there already in the 19th century. Gödel could have produced them before. I mean, so in fact, they could have been earlier. There's nothing which depended upon our physical understanding. That's all I mean. So I don't quite see your argument saying that these ideas were needed to cope with things that, like quantum mechanics, which are hard to understand. Okay, we need mathematics for it. That's true, but a lot of the mathematical thoughts came about from much more things that we would consider not hard to understand, I suppose.
I'm trying to think of something useful, like getting your dinner.
Yes.
As opposed to a game,
yeah.
So much of geometry seems to be other than...
Well, it's an interesting question. I mean, how did an ability to do mathematics come about through natural selection? And I think the good sound example is a nice example of something where we can understand it. Okay, I didn't give you a full description there, but it's something that we are capable of understanding why it's true. Yet, how did that come about? Through natural selection. It isn't something that our ancestors needed to know about in order to catch mammoths or something. But what my argument is that we're really using something in our understanding of even something like Goodstein's theorem, which is already present in building mammoth traps. I mean, it's a quality of understanding which has a much broader scope. I mean, it can be applied to all sorts of things. Mathematics is just a particular thing that it can be applied to. So my position would be that there isn't anything really special about mathematics. Okay, it's more, as I say, it's more abstract, it's more complicated and all sorts of things like that. But it's not essentially different from the kind of understanding that's involved in other things which were selected for, and which I would argue, not just human beings, I think other animals have developed something of that quality. And even they can do arithmetic too. I mean, you know, there are tests that chimpanzees and things you can actually get them to do even though they can't speak. So there are tests to show there is something there which seems to be not just a recent thing. That's all I'm saying. It's not just to understand modern physics or something. It's been there with us. There's probably not that much difference between us and go way, millions, I don't know how many years back into history. It's probably not that much difference.
Would an idiot savant with mathematical ability operating only at the computational level with no awareness but no understanding?
I mean, I don't know. I mean, it's possible. I mean, a lot of things are certainly done without the understanding. And sometimes things are done very well without understanding. Because, I mean, often it's, well, if you learn to drive a car or ride a bicycle or something, first of all, you're thinking what you're doing all the time, you see. And then it becomes what's called second nature. Well, in fact, it's probably a different part of the brain which is involved. Because initially, you're doing something with probably the cerebrum. And then after a while, it's the cerebellum which takes over. So I don't know, in your case, whether an idiot savant would and many of the people who were good at doing calculations weren't particularly intelligent in other obvious ways, although some were. And one example of Aitken, who was a very good mathematician, and he could do this too. So I don't know if you can generalize. But it's just an interesting example, because I had this put to me by a well-known physiologist who was he was in his 80s, I think, and he put this to me. He said, "There are these people, just as you mentioned here," and it was almost it was really the argument on the other side. How could they, if it was just computing with neurons, knowing the speed of neurons, which is slow, how could they do it? Because if they were just computers, operating as computers do, at the speed of neurons, they wouldn't be able to do it. And he made quite a good case for that, which would rather suggest that there is something else which is not just computation, even in that case.
Just getting back to what you were saying about the microtubules and the quantum computing.
Yeah.
What do you think that means as we move into the future? We start to learn how to harness those types of things and build more and more sophisticated quantum computers.
Sure.
Number one is, what do you think that means for the very definition of computability? And number two, what do you think that means for, as Ray Kurzweil suggests, the ability of computers to pass very sophisticated Turing tests?
Yeah, that's a good question. If we just take quantum computers as we understand that term now, it's not supposed to do anything outside the realm of computability. So I didn't mention that point, but it's actually a relevant point to what I was saying. So if you like, if you're staying down here and just using, where I can find that translation now, the conventional one, where you use the ordinary R procedure to get up here, which is just making a measurement from time to time. And ordinary quantum computers only do that from time to time. But, and they don't use it in the kind of way that I would need for this. So quantum computers, as we understand that term now, would not get us outside the realm of computability. Although it does get us outside, I mean, it addresses things like complexity theory, how fast you can do a calculation, which you could do more slowly by an ordinary computer. So what one would need to get outside the normal notion of computability is something which actually uses this scheme here. Now, since I'm saying it's part of physical action, I am saying that I have nothing against, I mean, I morally have something against it, but I have nothing against, as a scientific physician, somebody, some latter-day Frankenstein, building in the lab something entirely inanimate, which would take advantage of this kind of physics, and which would actually be aware, would be conscious, would be able to do things which I say non-computable, and would be conscious. I have nothing against that. So, okay, whether you like it or not, I think we're a long way from it. So I don't think there's any remote prospect of that in the foreseeable future. I mean, not in the foreseeable futures. Even quantum computers, I mean, okay, they have this program to try and factorize 15 or something, and they're nowhere near it, you see. So, yeah. 30 years. Well, yeah, maybe they do it in 30 years. But 15, you see. Yes.
Can you elaborate a bit on your common involvement structure in dumbbell?
Yes.
Especially with the characteristic time for
Yes.
dumbbell state.
Yes.
Where the obvious time would be the time for
Yes, the question has to do with the time in my scheme for reduction of the state, where I've replaced the cat by one lump. It's not a dumbbell, there's only one lump, which is in a superposition of two different places. And the statement is that if you put it in that superposition, it will, after a certain time, which I could calculate, be one or the other. So it would exist in the superposition for a bit and then flop over to one or the other. But for a thing, any sizable size like that, it would happen virtually instantaneously. So for anything the size of a cat or even a few cells of a cat, it would flip over instantly. So you need to have something much smaller than this. Well, I don't know how big that is in the picture, but certainly not a baseball or something. It would have to be, well, in the time of experiment that I have in mind, which maybe could be done, and there seems to be a genuine prospect of doing experiments in the foreseeable future, which would test this idea, it would be something like a little crystal of about the size of a speck of dust. And you would put that in superposition of two places which only differ from each other by something like the diameter of the nucleus. So it's not much. But that you hold it there and see whether it will maintain its superposition while you keep it correlated with something else. And then you bring it all back again and see whether you have lost your coherence or not. And my argument would be that in about a tenth of a second, that little speck of dust should become one or the other. And you can tell that in an experiment. So that gives you some feeling for the scale. A little speck of dust, something like a tenth of a second. But details, I'd have to fill that out a bit more.
And the time is estimated on the basis of gravity.
Yes, that's a point.
Same in the brain.
Yes, which is, of course, people can make fun of me. Oh, you think it's quantum gravity. Which, it's funny because I was giving a lecture once, and I was sort of hovering on something. And after at the end, somebody who was obviously a nutcase came up and said he had this theory that one half of the brain operated by quantum gravity and the other by quantum electrodynamics. Oh dear. But yes, the idea is that all state reduction is gravity. Yeah, on this view. So gravity is different, and the reason it's different is because it actually does affect space-time structure, whereas nothing else directly does. Yes. Sure. I know, yes. Yes. Well, gravity has this curious feature of being just like all the other forces of nature and also completely different from all the forces of nature. So it depends on how you look at it. Yes. No, okay, perhaps we shouldn't get into that argument. But it is the only thing which directly affects space-time structure. Other things do indirectly through their energy momentum, whereas gravity has this direct effect on space-time structure. So the argument I'm giving, which I gave yesterday, which I don't think I'll try and repeat here, was that the whole issue of whether something is actually stationary or not is put into question. And there's some extra element you have to take into consideration, which is where this instability comes from. But I agree, it's an unconventional view from the point of view of what most people do in quantum gravity. So it's, yeah.
One thing you didn't explain is why reduction of this nonlinear effect that would accomplish reduction of wave packet would be able to non-compute.
No, I agree with you. And that's where I use the weak Sherlock Holmes argument. But it's not anywhere else, you see. The only positive...
It might make it worse.
Yes, well, you see, it might. And maybe the mystics are right, and it's not physics at all, you see. But I think I agree with your question. That is to say, we should look in a positive sense for something which might be non-computable. And what's interesting, although I'm not quite sure how relevant it is, what's interesting is that there are only two places, or actually there are three, but two of the three places I've ever seen anybody in physics mention non-computability as part of what they were discussing has been in quantum gravity. And one of them was Jim Hartle and Bob Gerlich, where they talked about counting four manifolds, and it was a question of whether you could solve the equivalence problem as part of that. And that's known to be a non-computable problem. So they actually ran up against that problem. And the other one is a discussion by David Deutsch, where he actually brought this up. The one which is not gravity was one by Arthur Komar, where he talked about it was general quantum field theory systems. But I think in all three cases they were trying to say they didn't believe it. So I mean, it was, I don't know whether Gerlich and Hartle were trying to say they didn't believe it. It's just that they ran up. Well, I could ask Jim, not trying to put words in your mouth. But as far as I could take, I took your position to be on this, that if you do it this way, you run into this non-computable problem. And perhaps you better speak for yourself. Yes. Yeah.
Physics would have this property. But our argument also was that just because a number is non-computable doesn't mean that you can't compute it.
I think you lost me just there, but, yes. Yes, okay. Yeah. Yeah. Sure. Yeah. Yeah, now, I think I wouldn't think of it in terms of computing numbers, but that's perhaps another issue. No.
And for the purpose
Yeah.
of evolution, you don't need a computer that's always right.
That's true. So this is actually one of the things that I had to address. I mean, that it might make mistakes. It's certainly a big issue in Chapter 3, Shadows of the Mind. But that's absolutely right. You have to worry about mistakes. And Turing's own let-out, because he was well familiar with that argument, was that what distinguished human beings basically from computers was they made mistakes. And you can take that as you will. Yeah.
Maybe that's in fact important.
Yes, well, he argued it was important, certainly, yes. I suppose I find I'm a bit skeptical that that can be the real reason, but that's not.
Right in the back.
Yes. Yeah. And in that example, what it shows is that the rules of mathematical induction, or piano arithmetic, first order, mathematical induction, are not sufficient to establish the Goodstein theorem. But as I remarked, I mean, you can still prove it. But you prove it not using those rules. You use rules outside that system. And so I think the question you're asking is there always a broader system within which you can prove anything which is true? Well, you see, the trouble is, how do you know whether to trust your system? There's always going to be a broader system because your system could just assert this particular statement. But how do you know whether to trust it? The problem is always, if you like, a question of belief, or whether you think an argument is an argument, whether it's a mathematical demonstration. So it's a question of belief, if you like. And what Gödel shows is that however you try to encapsulate what you're prepared to believe as a set of procedures which are unassailable in mathematics, that you must be able to go outside. I mean, he shows you how to go outside it. So if you say this is what I'm prepared to use in my mathematical arguments, and you sort of lay that down as some well-defined computational system, then Gödel says, nope, you have that, you must believe something outside that. So it is, in a sense, that the problem is not whether there exists a system or not, or whether you trust the system. And that's a bit hard to formulate. That's I don't know if I've answered your question, but and in fact, Turing, one of the big things he did was to consider this sort of stepping up, Gödelizing, and going on and on and on. And he wrote a paper which is perhaps not quite as famous as it should be. It's a very good paper, in which he studied this whole question of sort of hierarchies of computation, beyond computation, and so on. And it's, again, an issue which comes into all this discussion as well.
I'm curious about, it seems like you make an assumption. I'm wondering if this is an assumption that you're showing because it's non-computable, but you have them non-computable. Are you also suggesting, or it seems like you're suggesting that it could not be associated with as yet undiscovered physical interactions?
Well, it could be undiscovered. Sorry, it's not as yet. It's not. I'm trying to say it's not within the scope of the physics we understand now.
Right.
But that it's not. I'm saying it's not outside the scope of physics, of some future physics.
Right. I guess
Yeah.
my question has to do with the differentiating between you're using the same group of physical forces, the same basic physical interactions, with different understanding of the implications of that.
Well, my position is not. I think perhaps the word interaction is a little misleading, because in physics one has the idea of certain kinds of forces, you strong, weak, and so on. And what I'm really arguing is it's not in that, in a sense. It's in the procedures we use the general quantum mechanical procedures that we use, and that there is a limit to those procedures, that we use an approximation to them which has this linearity property, and that when we apply it correctly to gravity, and this is where, you know, some people here will probably jump on me, but if we apply it correctly to gravity, I would argue, we're going to need this extended version of quantum mechanics, which has non-linearities actually in the quantum mechanics. So it's not so much that there's a new interaction we don't know about, because we know about gravity, but it's in the procedures of quantum mechanics that I would argue there is something outside what we use at the present.
And furthermore, the brain is quantum mechanics.
Yes, and that is also a thing which a lot of people have trouble with. If you talk to people who try to model consciousness or something or other, and you try to suggest that there's something quantum mechanical going on, they will throw their hands up. And, well, there's a sort of irony there because, of course, they're using quantum mechanics in the chemistry, which they would admit is there all the time. But the question is whether one is using a sort of large-scale coherent effects. And that's where I think people would, quite rightly, put a big question mark, because it does require extreme circumstances which are very hard to produce in the lab. We probably wouldn't even know how to do it at brain temperature. So okay, they're quite right to be shocked by this. On the other hand, I'm saying coming from the other reason, because of consciousness, I mean, how do you produce consciousness anyway? I mean, that's a shocking phenomenon. I'm saying that it must be there. And it's interesting that there are actually some experiments which might directly test this, which would see whether there are EPR effects. And it's a very ingenious idea that was put to me some months ago by an Australian called Andrew Duggins. And I want to, in a few months, I want to think about it seriously, because I think he had some very interesting ideas having to do with what's called the binding problem. When you look at something, an image that you see is made up out of all sorts of things. And part of this is color, which is one part of the brain, and other parts are movement, which is another part of the brain. And nevertheless, you see one thing. When you have a conscious perception of an image, the color and the perception all integrated into one thing. And the question is that process something which you need these quantum mechanical entanglements to understand? And he is trying to argue that you do need that. Yeah, that's right. It would be invoking the Bell, the Bell inequalities. And I really think it's a fascinating idea. I'm not sure he's right, but he may well be. And it would be a great step to see if that's right or not.
Why quantum mechanics rather than some sort of massive parallel mechanics? After all, when I'm doing quantum computing, right now, when I'm doing computing of a quantum problem,
sure. Yeah. Yes. But that, of course, it's related to a previous question. The quantum computing, as straight as we understand that term now, can be understood, can be simulated by a classical device. As you say, massive parallelism. You need a very, very massive parallelism. But nevertheless, you could still do it on a classical device, on a classical computer. So that's, if you like, one of the reasons I'm saying it's not just we need quantum mechanics. It's not just that with the standard reduction process. We need this. Yes, I mean, you're suggesting that it's just a question of making some very sophisticated computer. But what do you mean different, you see? Is it... because any computer, no matter whether it's parallel or what have you, is a Turing machine. Okay, it's an approximation to a Turing machine, if you like. Yes. And there is this issue about continuous, and there are discussions about that. In fact, there are notions of continuous computation and so on. But usually people, the line people usually take is that you could accurately enough simulate continuous systems discretely. Now, there's a question there. I'm not saying that that's clear cut. But I don't see even how you do that in practice, because you need to discretize to make sure you've got a decent answer. And the way one does computations, okay, if quantum computation was done effectively, it still is a computation in the ordinary sense. Sure. Oh, I see. Well, that's what, if you like, that's why I had to turn to the mathematical argument. But then you have to go through all the Gödel stuff, you see. Because that is trying to show you, I mean, okay, it's not a straightforward argument, but that is showing you that if you had a device which was ultimately a Turing machine to try and imitate what we do with our understanding, well, that it wouldn't work. That's what I'm saying. There are certain things it couldn't do. And I think I just have to refer you, first of all, to that, that web, the psyche thing, and then maybe Shadows of the Mind, if you can work your way through it. But it's tough going, I admit. but these questions are addressed. Okay, you could read it and then disagree with me, but they are addressed there. Yes.
Do you consider neural network computing?
Yeah, certainly. Yes. You see, a neural network is something that, and often they make devices specifically to carry these things out, but just as often it's simulated on a general purpose computer. And if you can simulate it on a general purpose computer, it is a computation. That's the easy test, if you like. So it's computation.
You can simulate neural networks on a computer.
Yeah.
Why is it not computable?
It is. It's computable, yeah.
But I thought that your intention was that you needed to go beyond.
Yeah. So I'm saying that what we do is not what is... maybe you see the term neural net, maybe that's a little confusing here, because people use that for certain devices, which are what I would call purely computational devices. They're models of certain types of mental activity. Okay, they may be quite good ones for certain things. In fact, an awful lot of processing that's done in the brain is unconscious. Maybe the entire action of the cerebellum could be simulated in some way by what we call a neural net. I don't have anything against that, because apart from certain things people tell me more recently, as far as I know, the cerebellum acts unconsciously. At least that's certainly the traditional view of it. Yet, nevertheless, there are certain other parts of the brain, certain other actions of the brain, which seem to be conscious. And I'm only addressing those ones. And so what I'm trying to say is that those actions are not things that you could even adequately imitate by what we call a neural network or neural net. So there's something else going on.
But
right.
Is it provable that a Turing machine or a neural network couldn't be trained to come up with the right answers with some non-perfect efficiency?
Well, that's all part of the argument. Yes. Well, I think people would... all these things have rough edges. So whether there are theorems, which whether you say it applies because the statements are woolly in certain ways, and so you might say it's not. But yes, there are theorems. I've made statements in my book which are claimed to be addressing this kind of question directly. But then, maybe people would question some of the... They're not... you always have to resort at some point to say something is unreasonable, because you're never quite sure what things are involved. So there's always a gap between the mathematical result and how it's to be used.
Question about randomness.
Mm-hmm.
Yep. We can create a random event now, the shape of which occurs in one and so many
Yes.
And consciousness has nothing to do with it. We can study that event. I think you're dealing out a brick hand.
Yeah.
And the chance of that particular brick hand occurring is one in, I forget the number, division.
Okay.
Second, on the biological level, there can be a pesky fly. And I keep swatting at that fly, and I keep missing. And now we can analyze biologically in that. Does that fly really know that someone's after him? And is he trying to evade that? Or what's it responding to? We can do all sorts of biological analysis. What I'm suggesting is there are different levels at which one can look at these random events.
And you're saying that the fly is acting randomly or not? I'm not quite sure I have the point of what you're saying here.
Well, I'm saying that
Yeah.
when you're looking at a fly,
Yes.
you miss them
Yes.
quite a few times.
Sure.
And the question I'm raising biologically is the fly evading your spot? Or is it just randomly leaving the event go to keep us a little breath of air?
Well, of course, it might be lucky. You know, he just happened to miss it. I mean, you could apply that to also the, and that kind of thing has to come into these discussions when it's related to your question about making mistakes and so on. And it may be that just by chance you happen to get it right every time, you see. And that's, so one has to talk about one's understanding of why you get it right and not just the fact that you get it right most of the time. So, I mean, these questions are of relevance. And, yeah.
Call this to an end. You're all welcome to